Welcome to my channel. So today let's have a look at problem 684, redundant connection. So for this problem, we're going to share a unified solution. First, I'll read through the statement of the problem and then do a simple analysis about the example and the method. And finally, we share the code and do the tests. Let's look at the statement of the problem. So in this problem, a tree is an undirected graph that is connected and has no cycles. We are given a graph that started as a tree with n nodes labeled from 1 to n. So here, notice the label indexing from 1 to n, with one additional edge added. The added edge has two different vertices chosen from 1 to n, and there was not an edge that already existed. The graph is represented as an array edges of length n, where the edges I equals ai bi indicates that there is an edge between nodes ai and bi in the graph. So that's the main statement. So we are required to return an edge that can be removed so that the resulting graph is a tree of n nodes. So if there are multiple answers, return the answer that occurs last in the input. So let's look at example 2 first. So these are the edges, and this is a depict of the graph. So from the graph, so we see that there are cycles in 1, 2, 3, 4. And here the output is 1, 4 because due to the order of edges appearing in the list. So so if we actually delete 1, 4, so this is a tree, and also we can delete 1, 2, and 2, 3, or 3, 4. Both in all the cases lead to a valid tree. Here is the constraints. So the n is the length of the edges list. So n is less or equal than 1000. So and there are no repeated edges. So this is an important assumption. And the given graph is connected. So yeah. So we will emphasize on this one. There's no repeated edges. That's important for us to use the unified method. So let's look at the method. So here, so with this problem, actually, first I want to make a definition of that's a tree. So a tree actually is a connected graph with n-1 edges, where n is the number of nodes. So there are two assumptions in the definition. So first, it's connected. Secondly, the edges and the nodes satisfy the relation that there's one edges less than the number of nodes. So with that said, I guess for this problem, the main effort is going to eliminate possible cycles. So with that said, I guess the natural way for solve this, like traversal algorithms, or here we're going to use unified, so which is very natural. So unified actually tries to find the connected components. So in this case, we only have one connected component after we do the union operations. So once we get the connected component, if we continue adding edges to the tree, to the graph, we will see the new edges have the property that the two nodes will already in the same component, which indicate that the ending of this new edge will result a cycle. So that edge is the edge we want to return. So here actually there's one sentence on the return which sort of confusing. If there are multiple answers, return the answer that occurs last in the output. So for the union find solution, it actually really depends on how we interpret the last or first. So if we are not absolutely sure, so we can actually do a traversal from the beginning to end, and then or from the end to beginning, and compare the smaller index, then return the edge, the corresponding edge with smaller index. But for our purpose here, we just want to demonstrate the use of union find, and so we will not focus too much on this. So as we have practiced quite a number of such problems, I will directly go to the implementation of the union find within the function definition, and then I will do the actual work for detecting the redundant edge. So first, I'm going to make some preparation. So for this, I'll first check how many edges we have. So this is the number of edges. So because there is one redundant, so this n will be the number of nodes in the tree, right? So with that said, I also want to initialize a root dictionary. So like this, I for I in range from 1 to n plus 1, due to this assumption, with node labeled from 1 to n. So here we want to implement union find in a very vanilla way. So in other words, we do not need to use path compression or union by rack. So due to the assumption that the length is less or equal than 1000, it's a small number. So we do not need path compression or union by rack to accelerate a little bit. So with that said, let me first implement a short find function. So find the root. So here, this is the very straightforward function. We are going to return I if roots I equals I. Otherwise, we are going to return find, so applied to its parents, roots I. So that's the implementation for the find. So now also let's do the union. So ig. So for this, I'm going to first find the root of node I and node J. So root I, root J equals find I, find J. Then we're going to check if they are already in the same component or not. So if root I does not equals root J, meaning that they are currently still not in the same component, we want to try to connect them. So by setting the roots, say root J equals root I. You can do the other way around, so both are okay. So that's about it for this. And for convenience, I want to do another operation, that is same root for ij. So just to check if the two nodes are in the same component or not, we are going to return find I equals find j. So this is the Boolean function checking if the two nodes are in the same component or not. If they have the same root, meaning that they are in the same component, otherwise not. So with that preparation done, I'm going to do the real work, the actual work. So we're going to traverse the edges from the left to right. So for edge in edges, so we'll call ij is the two ends. Then we're going to check if they are in the same connected component. If so, it means that this edge produces produce cycles. We are going to return this edge. So if same root, this ij, then we are going to return this edge. So otherwise, what we want to do is we want to union this two together, right? So because for a tree, for a valid tree, the final connected component is just one. So with that said, we are ready to return the we are ready to check the code. That's the full code. So consisting of two steps. First, preparation and implementation of our vanilla union find utility functions, and then we're going to do the actual work and detect the redundant edge. Let's do a check for the special case. It passes the special case. This is actually the example 2. So now let's check generic case. Yeah, it passes the generic case. So to get a better understanding, let me mimic the process and printing out the procedure. So in other words, I want to print out the root status. So roots after each union operation. Let's test this for example 2. So you see, the first one we add 1, 2. So 1 and 2 have the same roots. And in the second step we add join 2, 3. And 1, 2, 3 have the same root, that is 1. In the third edge, so we add 3 and 4. So we have 1, 2, 3, 4 have the same root, and then we add 1, 4. But 1, 4 already have the same root. In other words, they lie in the same connected component. Then we add this 1, 4. It's going to produce a cycle, so we return this 1, 4. So that's the main procedure for this problem. So this problem actually can be solved by traversal algorithm, but essentially plays the same role. But the union find is a natural suit for this problem. I guess that's about it for this problem. Thank you.